Hello everyone and welcome back. Today we're going to introduce two different types of matrices that are very important in application, known as orthogonal matrices and orthonormal matrices. Just for the record, some literature does conflate these two terms into one. Some people will call an orthogonal matrix one that satisfies the properties for which I'm defining to be an orthonormal matrix, but generally speaking, these concepts are subtly different, but I just want to define them in a separate manner just to avoid any ambiguity or confusion. So let's get right into it. So let's assume that A is an m by n, so not necessarily a square matrix, whose columns are named AJ, where J ranges from 1, 2 down to n, where n is the number of columns. Then we say that A is an orthogonal matrix if each of the columns within that particular matrix A are orthogonal to one another. That is, if you take the pairwise dot products between the columns, you will always get 0. And keep in mind, don't take the dot product of a vector with itself. Now, we say that a matrix is an orthonormal matrix if A is, in addition to orthogonal, all of the vectors and columns within that matrix A are unit vectors. Okay, so all of the vectors are orthogonal and each of the vectors are unit vectors, i.e. all of the vectors are orthonormal to one another. Now that we know what an orthogonal and an orthonormal matrix is, let's dive right into the first theorem about orthogonal and orthonormal matrices that we're actually going to take a lot of advantage of a little bit later on. So let us suppose that A is an orthogonal matrix, or an orthogonal m by n matrix, whose jth column is, say, AJ. And what we're actually going to consider is the matrix A transpose A. So we've already actually proven that if A is a rectangular matrix, then A transpose A always is 1 square and 2 a symmetric matrix. So if A is an m by n matrix, A transpose is an m by n by m, therefore A transpose A is going to be an n by n matrix. So it's going to have the same number of columns and the same number of rows as the same number of columns in the original matrix A. So when we look at the transpose of A, what will it look like? So it's going to have the first column transpose, the second column transpose, all the way down to the nth column transpose, and then we're going to be multiplying this by A1, A2, all the way down to AN. Okay, so what are we looking at here? Keep in mind this is an n by m and an m by n, resulting in our n by n matrix. So what does our n by n matrix looks like? So that's going to be A1 transpose times A1, A1 transpose times A2, all the way down to A1 transpose times AM, and then A transpose times A1, A2 transpose times A2, all the way down to A2 transpose times AM. This is continue all the way down to AN transpose times AN, A1 I mean, and then AN transpose times A2, all the way down to AN transpose times AM, and that's going to be our n by n square symmetric matrix, right? So nice square matrix. So one should be able to show that AI transpose AJ is always equal to AJ transpose AI. Nice little exercise there. At least for the assumption that these are orthogonal to each other. All right, so what is that going to be? So if A1 and A2 are orthogonal to each other, their dot product, which is another way of writing A1 transpose times A2, is going to be equal to 0. So all of these elements here are going to be equal to 0. So 0, 0, 0, and 0. Now what's going to go on the diagonal entries? So remember, if you take a vector transpose with itself, that's actually equal to the square of the norm. So if we look at this particular matrix in a simplified version, then this is precisely equal to the norm of A1 squared, 0 all the way down to 0, and then the norm of A2 squared all the way down to 0, and then 0, 0 all the way down to, put my dots everywhere, and then this is going to go all the way down to the norm of AN, the quantity squared. So this is under the assumption that A is an orthogonal matrix. Notice that if we impose, so A orthogonal, so if we impose that A is orthonormal, then what will the norm of these AJs turn into? Well, that's going to just turn into 1, 0, all the way down to 0, 0, 1, all the way down to 0, and then all the way down to 0, 0, all the way down to 1, which was precisely equal to the n by n identity matrix, right? So that's pretty much a sketch of the proof of the first theorem that I want to formally state here. So theorem 1. So theorem 1. If A, m by n, is an orthonormal matrix, then A transpose A is the n by n identity matrix. The next theorem that I want to take a look at is probably the most iconic theorem associated to orthonormal matrices. So let's assume that A is a square orthonormal matrix, and we're interested in finding, say, the inverse of that orthonormal matrix. In fact, if A is orthonormal, we can actually find the transpose of A, and that actually is equal to precisely the inverse of A. And that should actually be pretty amazing to you because we already know finding the inverses of generalized matrices, especially if n is arbitrarily large, can be extremely tedious. But if we know that A is an orthonormal matrix, then finding the inverse of that is as trivial as finding the transpose of that matrix. So let's go ahead and see if we can prove this very iconic theorem. So let's assume that A is an orthonormal square matrix. So if A is an orthonormal matrix, then we've actually already shown that A transpose times A is equal to the identity matrix. So this property actually should already be hinting at the fact that A transpose is actually the inverse of A, which is actually what we're getting into, right? But that's not exactly what that says, because it's possible that A times A transpose also, or also doesn't give you the identity matrix, which would violate the property of inverse matrices. So if this is true, which we've already proven, let's find the determinant of both sides of this equation. So that means the determinant of A transpose A is equal to the determinant of I. So the determinant of the product of matrices we know is going to be the determinant of A transpose times the determinant of A, and that's going to be equal to 1 because that's the determinant of all identity matrices regardless of size. And what we have here, so notice that A is the determinant of A is a number. The determinant of A transpose also is equal to the determinant of A. So what we have here is the determinant of A times the determinant of A is not equal to 0. So if the product of two determinants is not equal to 0, that means the determinant of A is not equal to 0, which means that the inverse of A exists. So if the inverse of that matrix exists, then we can perform some algebraic manipulations to that particular statement, A transpose A is equal to I. In particular, if A transpose A is equal to I, what I can do is I can multiply both sides on the right-hand side by A inverse. So it's going to be I times A inverse on the right-hand side. And then we can associate those first two, and then we see that A transpose is actually precisely equal to the inverse matrix. So if A transpose is equal to A inverse, that means, of course, that A inverse times A is equal to I, and that's, of course, going to be equal to A times I inverse, or equivalently, A transpose A is equal to AA transpose is equal to I, which is what we sought out to prove, right? So if A is an orthonormal matrix, then the inverse of that matrix is precisely equal to its transpose. Now, within this theorem, we actually used a very interesting observation. In particular, notice that we have the determinant of A times the determinant of A is equal to 1. So we can actually have a nice, I guess, sub-theorem, or some people will call it a lemma, and precisely if A is orthonormal, then the determinant of A is actually equal to plus or minus 1. So how do we go about proving that? So using pretty much the same starting steps as before, we already know that A transpose is actually equal to the inverse of that matrix. So let's actually approach this from a different angle since we already know that that is true. So if that's the case, that means the determinant of A transpose is equal to the determinant of the inverse. By properties of determinants and transposes, we know the determinant of A transpose is just the determinant of A, and the determinant of A inverse is 1 divided by the determinant of A. Solving that equation for the determinant of A, notice we have the determinant of A, the quantity squared, is equal to 1. And then we can take the square root of both sides of that equation, and that's going to give us the absolute value of the determinant of A is equal to 1, which means the determinant of A is equal to plus or minus 1, which is what we sought out to prove. So these two theorems are very, very special when it comes to orthonormal matrices. Now that we have a theoretical understanding of orthogonal and orthonormal matrices, let's look at an applied example. Suppose we have this 3x3 matrix given as so. Let us assume we want to find out, is this matrix an orthogonal matrix? Moreover, is it an orthonormal matrix? So how do we go about finding that? So the first thing that we need to figure out is, are the columns of this matrix pairwise orthogonal to each other? So let's call that A1, A2, and A3. So what is the dot product of A1 and A2? So that's the dot product of column 1 and column 2. So we know that that's going to be equal to 2/3 times 1/3, which is going to be equal to 2/9, plus negative 2/3 times 2/3, that's going to be equal to minus 4/9. And then 1/3 times 2/3, that's going to be equal to 2/9. And when we add those together, we have 2 minus 4 plus 2, that's going to be equal to 0/9, which is equal to 0. Now let's look at 1 and 3. So 1 times 3, that's going to be equal to what? So that's going to be equal to 4/9. And then plus negative 2/9 plus minus 2/9. So we have 4 minus 2 minus 2. That's going to again give us 0/9, which is equal to 0. And lastly, we have 2, 3. So how many different pairwise dot products do we need to do? We need to do 3, choose 2, right? So 3 factorial over 2 factorial times 3 minus 2 factorial, which in this case is equal to 3. Right? Just in case you have an arbitrarily large matrix, you don't want to miss any of those dot products. So lastly, we have 1/3 times 2/3, that's going to be equal to 2/9, plus then that's going to give us 2/9, and then minus 4/9, which is 2 plus 2 minus 4, which is equal to 0/9, which is equal to 0. So if the dot product of each of the columns is equal to 0, then that means this matrix, which I'm going to call A, that means A is orthogonal. Now just because it's an orthogonal matrix, that does not imply that it is a orthonormal matrix. Now we need to see that each of the vectors are indeed unit vectors. So we need to find the norms of each of those vectors, so let's go ahead and do that. So the norm of A1 is going to be equal to the square of each of the components. So that's going to be equal to 4/9 plus 4/9 plus 1/9, which is going to be equal to 4 plus 4 plus 1, which is going to be equal to 9 divided by 9, which is 1. So that's the square root of 1, which we know is going to be equal to 1. If we look at the norm of A2, that's going to be equal to the square root of 1/9 plus 4/9 plus 4/9, which is equal to, again, the square root of 1, which is 1. And the norm of A3, which is going to come out to the square root of 4/9 plus 1/9 plus 4/9, which again is the square root of 1, which is equal to 1. Therefore, the columns are unit vectors. So the columns are unit vectors. So if we have a matrix for which the columns are orthogonal to one another, and all of the columns are unit vectors, these two together will give us that A is an orthonormal matrix, right? Therefore, it's going to have several nice properties. So let's recall what that matrix A is. So A, remember, is the matrix 2/3, 1/3, 2/3, minus 2/3, 2/3, 1/3, and we have 1/3, 2/3, and minus 2/3. So we already know that this matrix is orthonormal. So what fun properties do we have with this? Well, we can ask, what is the inverse of this orthonormal matrix? Well, we know since A is orthonormal, the inverse of this matrix is precisely equal to its transposition. Therefore, the inverse of this matrix is precisely going to be equal to 2/3, 1/3, 2/3, minus 2/3, 2/3, 1/3, 1/3, 2/3, and minus 2/3, the transpose of the original matrix. And one can multiply those two matrices together, and you should be able to show that that is the 3x3 identity matrix. The next theorem that I want to sort of explore might be a trivial one based on the definition of what an orthonormal matrix is, but let's just state it anyway. So if A is an orthonormal matrix, then its columns form an orthonormal set of vectors. In particular, all of the vectors in that set are orthogonal or pairwise orthogonal to one another, and also unit vectors. So how are we going to prove this via the things that we've actually gone through so far without sort of exploiting the definition of what an orthonormal matrix is? All right, so let's get right into it. So we already know that the inverse of an orthonormal matrix is actually equal to the transpose of a matrix via that theorem that we just proved just a moment ago. So if that's the case, that means if we do A transpose A, that's always going to be equal to the identity matrix, provided that A is an orthonormal matrix, right? So pretty much we proved both of these two theorems slightly independently from each other. So that means if we look at the elements of A transpose A, it's actually just going to be equal to the elements of the identity matrix. So that means if you look at the jkth element of A transpose A, that's just going to be equal to 1 if j is equal to k, or 0 if j is not equal to k. Some people also just abbreviate this via the delta function jk. Right? So let's actually look at this from the vector-wise perspective. So we can actually look at this and say, okay, well that's just going to be equal to the sum from, let's say, I is equal to 1 to n of AJI times AIK. So we're looking at the rows and columns of A multiplied by each other. So again, if that's the case, that's also going to be equal to delta JK. So what do we have going on here? So we're looking at the rows and the columns of this particular matrix. That means AJ transpose times AK is also equal to delta JK. So that means if j is equal to k, that means the dot product is 1, and if j does not equal to k, then the dot product is equal to 0. That means that the set S containing a1, a2, down to an is an orthonormal set, which is what we sought out to prove. Now, the last thing that I want to do today is actually define another type of matrix, and this matrix is called a unitary matrix. So A is said to be unitary if a Hermitian A equals a Hermitian is equal to the identity, where the elements of this matrix A, J, K belonging to the matrix A belong to the complex set. So unitary can be thought of as, say, a complex analog to an orthonormal matrix. So from this definition, we see that if AHA or A Hermitian A is equal to the identity, that means the Hermitian of A is the inverse of A, right? So that means A Hermitian A is equal to the identity, which means that 1, the inverse of A is equal to the Hermitian. Now, if A is a real matrix, then that means A Hermitian is equal to A transpose, and that goes back to the orthonormal matrices. The second problem theory that you should be able to prove from this is that the determinant of a unitary matrix is always going to be equal to plus or minus 1, and also the columns of A, or the columns of a unitary matrix, form a orthonormal set. So it satisfies the same exact properties as a orthonormal matrix does, right? And I'll leave those three complex extensions for you as an exercise. So these are some of the important properties associated to orthogonal, orthonormal, and unitary matrices, which have so many different applications in a variety of fields, including linear algebra. So I hope to see you later when we expose these very important applications, but until then, I hope you take care. See you then.